almost anything, the derivations, the definitions, the proofs, algorithm. For example, I'll ask you, what does this mean? Okay, I'll ask you to discuss things and so forth. And because later part you do homework in groups, so that's why I say your group. What I find out is that you say like each group have three, you each one do a problem. That's okay, but then you have to discuss among yourselves. So that say suppose you do problem 1, you have to know what other people done for problem 2 and 3, because I may ask you on some problems. It happened that problem you didn't do, and say then you're disadvantaged. You see what I'm saying? Of course, it's a random process. I do not know which one you're doing what, but you do need to be familiar with all these aspects, because the problems really carefully chosen usually cover different aspects of these applications. So you really need to not only certainly the problem you did, certainly got into the detail, but the problem other people did, you also need to get into the detail to see exactly how it's done, why it's done this way, and so forth. Okay? So now you have plenty of time to prepare for it now, especially Monday's a holiday. So, okay. Bring your own answer sheets. I mean the blank sheet, because sometimes people come to the exam and say, "Oh, I don't have anything." So, okay, yeah. Is that okay? Good. Good. Well, you can get a sort of a very, these 5 chapters. The first week, is really each week sort of like a topic, so to speak. The first week mainly is about the I would say about the sort of floating point computation. That's the key thing is that in various aspects, every number has to be, especially floating point, has to be represented in the this so-called floating point representation, and this representation, whether it's an old one, new one, idea is still the same. You have certain bits have to be allocated for exponent, others for fraction. And no matter how you do it, you still have to have the base, the exponent part, the sign, usually which one gets, and the fraction. And how exactly, this is slightly different. This is so-called the algebraic standard, but the idea is still the same. You just scale it up. Some you allocated, the exponent gets smaller, but then it's more refined. The older ones, the exponent gets bigger, but it's more coarse. But it's always a trade-off. Trade-off in terms of accuracy and range, so to speak. But no matter what, the ideal, the principle is still the same. So that you have to be absolutely be aware of that. And there's some examples you have come through homework. You know that the usual arithmetical law doesn't hold in a computer. So it very much depends upon how you compute. You add things this way, you got one answer, add that way, you got another answer, and it all depends on how you code it. And there are better ways to code it. You want to avoid the cancellations. You want to add the small numbers to code first. Things like that. And those can be proved by what we call the error analysis. And there are some deterministic one, and there are some sort of probabilistic error analysis also. We did not have time to get into some of this detail. But I think I extracted all the essential things you need to know in there. You have to be aware of what's the range, what's the largest one, what's the smallest one. For that, you can be aware of this possibility of underflow, overflow. And each compiler has their own way to handle so-called exceptions. And depending on the compiler, just have to know. So that in terms of the first week. And then the second week, we enter into this optimization. Optimization of a deterministic type, also this is stochastic type. And there's a various kind, there's a univariate, a multivariate, there's a various kinds of methods you can and the point there is that, when you do the iteration deterministic type, usually it's local. And most of the time, it's try to find the extremum, the maximum, minimum, but all amounts to find the zeros of the derivative, so to speak. Unless, of course, you do direct search, and then you will not try to find the zero of the derivatives. But otherwise, you will try to find the zeros of the derivative. So in other words, you find the roots of something. And the roots, you find a zero, it doesn't guarantee it's what you want. It may be minimum, maybe maximum, maybe inflection points. You just have to test it out. So many times it's updating there. The basic idea is that direction where we move and how far do you go, so step size. And then there's various ways to determine that. Which direction, how far you want to go, how to iterate. Generally speaking, at the beginning, you want to probably take larger steps until you get to the ballpark, then you do smaller steps, and then you can do the local search. So most of the time, you do this, it's not just fixed, generally speaking. Mostly, you do the adaptive type. And the other thing is that it's always good to have a mini starting point. If you don't have any idea where the initial point should be, and then you should start from many different points and to see where you go. And if you can, always plot. But of course, for multi-dimensional, it's difficult to plot. And as I say, I always caution you, for multi-dimensional optimization problem, usually for complicated one, it's a very difficult problem. You have to be very careful. Do not just put in something in the computer, call it. There's all kinds of algorithms of optimization in the almost any package. So the tendency is that, I just use this package and do the sort of default type, because almost all these have a default parameters. It's tuning and so forth. Almost always have a default. It's just, just give the default, whatever come out, that must be it. Well, most likely it's not it, actually. So, and the other thing is always, for complicated problem, multi-dimensional, always need a double precision. Always. Many problems you can run the same thing. If you declare the double precision versus not, and one will converge the other one. So it's always do double precision. So that's in terms of the deterministic type. Then there's of course the combinatorial type or stochastic type of the optimization. And those things, of course, many times it may or may not guarantee the convergence. But because the problem is so complicated, you will be happy to get something close to it and in reasonable amount of time. So that's why there's a development of this either called the stochastic optimization or combinatorial searching type. The hope is that you get reasonably close, and for those types, usually you try to get the global tree. And for that, it's always advisable to start with many different starting points. Try many, and do the comparison. I'm talking about from the practical point of view. These are sort of course, there are many of these methods. The book, pick up a few, but there are many others out there. Okay. There's no end to it, actually. And as you can see, as you go, you can impose your own what you call this adaptive type. You say, well, for this one, I really should do this. But I always do it. You know, that's the whole thing about this so-called taboo type is that, well, whatever you think is reasonable, you post it. Okay? And that's how it's done. So those are in terms of the optimization type. And then we have the next chapter is so-called the EM algorithm. EM algorithm is a particular type of problem to handle the optimization when you have so-called missing data. Okay. The missing data is not necessarily missing. You know, actually, in one of these problems, oh, by the way, I should say, I have not completed reading your homework yet. It's taking enormous amount of time to read it. and many times I'm ready, you say, okay, this part is here, but the other parts in the code, you have to go read the code. And there, things got documented there. That gets even harder to read. So, but anyway, the EM algorithm, you know, for example, we do have a problem, what's this, 4.2, is that right? These HIV data, you know, essentially that's a mixture, 3 mixtures. And I noticed some of you try to do it into multinomial. But this problem they ask you is, of course, a Poisson and a mixture Poisson and so forth, and it can be, in other words, Poisson and the multinomial. Sometimes one can be approximation for the other, which is true. But this problem, they want to use the Poisson as an approximation for the distribution. The one is that the you know, those who always say 0, that's one group. So that's one population. And the other population is sort of an honest group or something like that, and then just a moderate type, and the other group is a high risk type. And so that's why you have essentially got 3 distributions. The high risk type is a Poisson with 1 rate. The middle one is a Poisson with another rate, and the other group, okay, it's just always 0. It's just well, how many of these with the probability percentage, they call it alpha with the indicator function. So that's really in other words, you want to estimate in a way, you know, given that data set, you want to estimate what is that probability distribution. Okay, so it's a mixture problem. So in mixture problem, typically it's the following. If you know the mixture parameters, like alpha beta in this case, of course the other one is 1 minus alpha minus beta. If you know the alpha beta, then the other 2, lambda and mu, are easy to estimate by maximum likelihood. And then put it the other way, if you know the lambda and the mu, the alpha beta become also fairly easy to estimate by conditional expectation. So this kind of problem is not really in terms of missing as such. But if you consider, let's say, alpha beta as something missing, and you want to use the conditional expectation to estimate the alpha beta. Once you have the alpha beta, you put it back in there, and then you say, okay, given this alpha beta, I'm gonna, and then the whole thing becomes complete, and then I can use maximum likelihood to estimate the lambda and mu. So you go back and forth. So this is the expectation for alpha and beta, and the maximization for lambda and mu. So this is sort of like you consider the alpha and beta as if they are not there. So you say, okay, since they're not there, I use the conditional expectation to estimate. And once I have that, I put it back in as if they're there, and then I just use maximum likelihood to estimate the lambda and mu. Once I have that, I go back to re-estimate the alpha and the beta. So you go back and forth like that as if it is, and then the algorithm becomes much easier. Of course, you can consider alpha, beta, lambda, and mu, all unknown. You want to do it simultaneously as maximum likelihood you can. Okay? But the problem gets much, much harder, computational speed. So this EM algorithm actually can be fairly wide. But I also have to say, not all the problems can be done by the EM algorithm. There are situations, I don't have time to show you the examples and so forth. The EM argument doesn't work. Okay, and there's always such a situation. So, as I mentioned to you, in this class we did a very broad survey of all the important computational statistics, or the statistical computing, however you put it. So all we can do is that give you what's the basic idea, and the most of the important theorems, so forth, we really can prove it. Time to prove it. And so, but as you certainly should know, almost anything, always under what? A set of assumptions. Okay? Anything we do is always under certain assumptions. What I do today, I made certain assumptions. I assume the sun will continue to come out, which is good assumption, but it is an assumption. Okay? All right? So we always do things. In the back of mind, there's always certain assumptions. We always have to keep that in mind. Some assumptions are quite reasonable, no problem. The sun will come out tomorrow. This is reasonably good. Okay, but some assumptions may or may not. They may have some chance, may not be there. Some maybe 99.99% is true, but with that one out of 10,000 times may not be true, and then your problem may be just one of those. You just have to be aware of it. In other words, this is very important. It doesn't mean that we have a procedure, it seems to always work. That's never true. Always under certain assumptions, that is true. But then you have to be careful, what are the assumptions when you always should check them. Okay? So, even like the secret methods and all these things, you can construct some weird problem, it just doesn't work. Okay? There's always this so-called pathological. Some may not be very pathological, but it still doesn't work. Okay? So that's in terms of this EM algorithm. It's still in the class of, you may consider that optimization type. Okay, to usually do the maximum likelihood estimate of something. So that's sort of in a group by itself. The first group of methods in the class of optimization. Of course, by optimization, it's a very important class of problems. And the second group was in this book called the Part 2 is the integration and the simulation. Now, integration have many different kinds, and the first week we talked about is the so-called deterministic type. Okay, the sort of Newton-Cotes type. Those are the equally spaced ones, and usually those you do what we call the composite method. You divide them into small intervals, and within each one, you apply certain things, and the sum up all the things out. And the second type of determinism is called the Gaussian quadrature, and that one is that you do not partition into the same, not necessarily the same length of the intervals, especially what we call these nodes are not equally spaced. But then in this case, it's allow the nodes to vary in that sense, and then you gain the extra degrees of freedom. But in those kind of quadrature, Gaussian quadrature, and then these composite methods gets complicated. Because each interval you got to rescale to know where it is and so forth, it gets complicated. So for the Newton-Cotes, it's very easy to write out, at least for Simpson's sake, certainly for trapezoidal or Riemann sum, that's very easily coded. But even up to Simpson, you can easily do the recursive ones to find a partition, and that's easily done. But for the Gaussian quadrature, it may not be easy. So typically for the Gaussian quadrature, you just use the higher order terms. Okay, instead of doing the composite, it means you chop off that, slice each one of them, and then each one do a Gaussian quadrature, then sum it out, because every one of them you got to rescale it. Okay, so this gets complicated. So you don't want to do that. So typical of, I'm not saying you cannot do it, okay, And some people may want to do that. If so, for some reason, the integration region, okay, you can naturally partition into several ones and take advantage of the spatial structure within that particular interval. Just 2 or 3, you probably can do that. But other than that, you don't. You just use the higher order Gaussian quadrature with a higher degree of polynomials. And typically these things, usually they are, as I said, calculated in terms of nodes and weights to fairly high order degrees. Those things you can just search out to find out. You usually publish this somewhere, and you can just plug it in to use. And actually, that's quite convenient. And usually you can get quite a high degree of accuracy. So that's in terms of deterministic integration. Integration, of course, any kind of expectation, variance, all these things is integration, okay? Because it is integration. So just and not to mention, of course, you have to find the so-called points of the confidence interval for special functions such as normal, t, chi-squared, so on. Of course, those special functions has been calculated use the spatial techniques to get very high degree of accuracy, spatial detail. It used to be, you probably very few of you, except in the usually Stat 100A, you have a table on the back. Nowadays almost nobody carries the table anymore. In our library, you have volumes of these spatial tables about the cutoff, this percentage point of that, volumes. People spend years to compile those kind of things. But of course, nowadays in the computer, in the handheld, all the programming you just punch in, gives the results. Okay. So those are the called the deterministic one. Then you have the stochastic integration, and those, of course, are multidimensional, highly complicated function or arbitrary ones, and then you want to get reasonably close to what you want, and then we have this so-called stochastic integration or probabilistic type of integration, and then those are called Monte Carlo, or by simulation, generate the random deviates according to certain distribution in the integration. But that's in chapter 6 already, isn't it? Yeah, so maybe I don't get in here. But I do want to, do you have any questions before I get into some of these homeworks? Okay, so let me talk about these homeworks. 4.1 asks you to do is that the problem says that in example 4.2 in this math problem, in addition to the original, how many of them? 622 sample, you have an additional 578 samples. But these samples, they only know it belongs to this area or this typical type. Other than that, in other words, this is a phenotype, that's all you can tell, and that's about it. And if those are additional data, and ask you to use the EM algorithm to estimate the maximum likelihood estimate of these PC, PI, and PT. So the only thing, of course, now you have extra data in here. You have these, what we call these. So now originally you have an NC, NI, MI, NT, right? All right. And now you have additional, this is called NU, this is 578. So you have an extra data. So the only thing here different from what you had before is that you do this, all this, as before. Now the question is, what do you do with this one? But this one, since this, you know this is the unknown, but come from the I and the T part. So this will contribute to what? To the IT and the TT. So this will contribute to NII, NIT, and the NTT. Okay? That will contribute to that. But in the same way, since these contribute to this, so you have what? This is this you have the PI squared, this you have the P twice PI, the PT, this you have what? PT squared. So, in other words, for this 578 condition on this, and then it's a what? It's a multinomial with 3 cells with these as the probability. Okay? And then whatever comes to here will add to what? These. Whatever comes to here will add to that, whatever comes to here will add to that in your equation. And that's all. Okay, so let me just put it this way. All you have to do is really, given all the conditional, given and used. Okay? The latent count, let's call it the NII under U, NIT under U, and NTT under U. This is a what? Is a multinomial. With probability or normalize the probability of this. I already summed PI squared 2PI PT and the PT squared. So you will do the same as you did, because for the previous one you have an NC here, and then you know the NC, you have an NCC, NCI, NCT, and those are the 3 multinomial, and these will be done exactly the same way. Okay? Will be done exactly the same way. So the only thing that change is what? These ones you have to add to back to those NII from what? From I, and then from NI, and okay, those from that, and those from NT itself, and so forth. Just add to it. That's all. Am I clear or not? Do I need to give more detail? So once you have done this, then what you can do, just say is that let me just do this. Number one, you still do as before. Okay. What condition on on NC and PT and T, and then you get this. You get the NCC at the time T, NCI at the time T, and NCT at the time T. Okay? And then number 2 is conditional on NC and the NI. Conditional on the NI, the PT, then you get the NII at the T and the NIT at the time T. Okay. And here is this, of course, originally of NT, that's just to the NTT. But then number 3 is that you conditional on this NU given the PT, you get what? You get the NII under U at the time T, and the NIT under U T, and the NTT under U T. But the way you get this is similar to how you get that. This one, the NC, we did not have anything. This one, just that. But with the NU, in order to say this NU contributed to IIIT and the TT, which is attaching U to it, means these numbers come from the U. Okay, the NU. That's all. So, so then what you have is that the N. So now NIIT is NII. Well, suppose I probably come from I. If I use the I, might be better. I to say this really comes from I. Okay, from NI. Are you following me?
NI and what?
Yeah, you know the conditional NI and the PT, or the PCP, capital T at the time T, and then you calculate all these numbers. That's a binomial, right? So you calculated these. That is, these numbers come from I, and these numbers come from U. Okay. And so once you have this, then the actual number, the NIIT, will be from the I part plus what? From the U part. NIIUT. That gives you the total from there. Okay? And then, and the NIT at the time T, this is NIT plus the NITUT, and the NTT at the time T, this is NTT. This is NTT of U plus the original NT. NT, right? Of course. Okay. Yeah, it's NT. Okay. So what you have is these ones you get from here, and then these ones you get from here. That's all. And it's just put 1, 2, 3, 4, 5, 6. Put this back into your equation, and then nothing changed. Okay. So I would say, and then here I would just say this. You substitute. Substitute 1 and 4. 1 means this 3, 4 means those 3 into that equation into 4.10 and page 101 to get Q. That's your, because there you have a formula, you need these numbers in there. And you just, you know, whereas before these numbers are these, whereas before those numbers just what? I, and the NT. But now, these 3 numbers, you have a contribution from U to that, from U to that, and U to this one. So you just modify the number, and that formula is still the same. And then you take the, since that formula is the same in this notation, and then all you have to do, take the partial derivative, the formula, the solution is still the same. Nothing changed. The only thing changed is that is, how do you handle this NU? How do you distribute this 578 into different categories? And that is by this. That's all. And once you have updated these numbers in this way, these 3 numbers in this way, and that number is still the same as this formula, and you take the partial derivative of this, and so forth, the formula exactly the same, nothing changed, except now you substitute with this, that's all. Okay? And then the M step. The M step, just use the 4.11 to 4. That's the same. 4.11 that's your update on the solution. Okay. Except that now this is defined by this. That's only difference. Okay. Okay, so that's a derivation in terms of the 4.1a. And the B says code this and get the ME with the iteration. Actually, well, the same as that. The only thing is that this number got changed, that's all. So the code is really the same. Okay. And the C says use a supplemented EM algorithm and to get the covariance function. And well, this you just follow the section 4.2.3.2. Just follow that, and using this gamma ij and so forth. You know, you have to do these iterations to find. As you do the iteration, gamma ij will approximate psi prime. Okay, because that's a component-wise difference quotient, difference quotient approximate the derivative. Okay. Any question on that? You know, for each iteration, you do one component at a time. Now, D says uses Bootstrap, and then, many of you just say use Bootstrap, but you cannot tell me how do you actually do it. You know, of course, in here, the Bootstrap is a simple one, at least in this section, because we haven't get to this chapter on Bootstrap yet. So in the book, it has a very short description, and that description, the Bootstrap, essentially says is to discard all the missing data, so to speak. You know, just sample the X itself, and you know, in that way, that's okay. But you have to tell me how do you do the Bootstrap, because Bootstrap in many different ways. Okay. And the E says EM gradient algorithm. Well, that's a fairly straightforward, because in this case, this Q double prime and so is easily computed. Okay, and actually the book already computed Q double prime for you. Again, the formality is exactly the same. The only thing that changes is these numbers. That's all. Okay, so the formulas really are all the same there. The gradient and the Atkin acceleration is the same. You know, again, there, all these are already given to you, so to speak. Now this Quasi-Newton, of course, you know, again, the book has a formula in there, and for this particular case, again, the B and the Q prime is already given to you, so you just follow that, update the little b and so forth, and then you can code that. So you know, for this part, it's really fairly straightforward. And then compare the effectiveness, efficiency, standard, and variance. Of course, this part, you know, some of you actually did quite a good job. You know, did some comparisons and so forth. But still, you know, many of you have quite good write-up, and for this part, simulations, some with color and so forth. But still, when you do this, you have to give the caption. Many times you don't tell me what's what. And then maybe it's absolutely clear to you, it's absolutely not clear to me. Because it's not write it, I haven't got the ability to do the mind reading yet. So I really don't know, unless you write it down, I really don't know what is what. Okay, so all the graphs, you have to have good caption to explain what is color, what's, you know, where you started it, and what is this, what is that, so that I can read the chart. Otherwise, you say, okay, we did a simulation to result in the graph. Well, but I don't know how to read the graph. And then maybe all the information is there, but I don't know. Okay, so you know, for this problem, some of you did quite well in terms of a lot of the simulations, which is good. Of course, all these methods, you do the comparison, and it's not easy because certain problems is more convenient for certain algorithm. And if we change a problem, and then another algorithm might be better. Okay, but of course it says for this particular problem, which one would be better. Okay, and then of course this also depends upon where you start and so forth. Step size, and but as I said, you know, some of you did quite well. Did quite a bit. Okay, very quickly, I'll give you some idea about this problem 4.2. The 4.2 is a mixture of I will do it differently from what you usually do, okay? Of course, you can always do what you usually do. Set up the likelihood, get the conditional expectation, and so on, okay? But I may do it slightly differently. And then essentially it just says the probability x equals I given the theta. And then this is essentially, this is proportional to what we call the pi I theta. X equal I, that means whoever in this responded, say I, 0, 1 through 16, right? The probability any respondent responded is I is proportional to this mixture density, which is alpha indicator of the I equals 0 plus the beta and the mu I e to the minus mu and then plus, of course, 1 minus alpha minus beta and the lambda I e to the minus lambda as a proportional. Actually, for this one, the normalizing constant is very easy because you know it's Poisson, so normalized constant is what? For each I, which is I factorial. Okay? So actually, you may say this probability, if you want to make it a bona fide probability, is really just what? I factorial of pi I theta. It's just normalized by I factorial, and then this is a bona fide. And because this is I equals 0, that's just 1 anyway, so it doesn't matter. But then each of these, you divide this by I factorial, this is what? The probability of, say, suppose we call this y. This is the probability y equal I, with the Poisson distribution with parameter mu. And this is what, this part, if you divide by I factorial, that's the probability of z equal I. That's lambda to the I e to the minus lambda divided by I factorial. So if you use this, you sum this, you sum over I equals 0 to infinity, you get 1. Okay? You get 1. So, because this sum up to 1, this sum up to 1, and then alpha, beta, the sum up to 1. Okay? So essentially, that's, so what I'm saying is this is actually this is actually density function, this is normalized and density function, this is actually density function. So this is the mixture of the 3 density functions. 2 of them are exponential, Poisson. The other one is a sort of a point mass. Okay? So of course here the theta in here is alpha, beta, mu, okay, of course, the data collected only as I goes from 0 to 16. You say, well, the Poisson actually I can go to infinity. But the thing is that once you know, it depends on these mu's, but when I gets very, very big, the tail is what? Very, very small anyway. So this is actually a good approximation, actually. Okay? Because originally, you know, the book says if you take the whole thing, use one single Poisson to approximate it, and then actually it's a very full fit. So that's why it say, okay, according to the prior knowledge, it says, okay, there are some people, they just don't, you know, they're cheaters, it's all kind of done it. So that's always, whatever you ask, they say zero. But some are honest ones, and they will give you some answer honestly, and these are the high-risk group, and you have a different rate. So that's why they say, okay, let's, you know, use these as a approximation, try to fit the data, see how well it can fit. So this is typically how the model goes. All right. So normalizing factor is really just this, but that's not the that's not important. But the important thing I want to tell you is that they want to model it by the mixture model. Okay. So then, so the likelihood of this is what? The likelihood is, of course, this is L theta given. You may say this N0 and 1 because those are the theta and 16. And then, of course, that's proportion of the product of I 0, 16 of the I theta. Now, you actually normalize it, and then NI. This means that, you know, out of that NI, that many people reported, the I, what?
I wanted to ask if aside, the pi I includes that alpha I when I is equal to 0, and
Yeah.
that's not Poisson, so that portion
No,
of it should
no,
be
this is a Poisson, that's Poisson, this is point max. No, mixture, you can mix any density you want.
But dividing it by the I that
No, no
portion
problem,
of I
because
factor
this
is-
is only I equals 0.
Okay.
So 0 factorial is 1.
Oh, of course.
Doesn't matter.
Okay.
Huh?
I said it's stupid of me to say that.
Okay.
You're true. Yeah, 0 factorial.
Yeah, because this doesn't contribute if I not equal 0. It doesn't matter. Okay? Yeah. Okay, so this is a, you know, because all the individuals are independent, so of course these got a the product of these, but all these NI that many individuals reported I, okay, and that's the probability. Any individual I reported I is with this probability, so that's what it is. Okay, and if a pi I theta divided by I factorial, that's a bona fide density function. Otherwise, you can consider the n, you know. Anyway, okay, so that's what it is. That's a likelihood. So now you take the log of the likelihood. So the L of theta given n0 to n16, and then that will be the summation I equals 0 to 16 of the ni log of the pi I theta minus log of the I factorial. So that's the log likelihood. So now, okay, let's just do this. Say, I'll do it my way, okay? You can do the conditional expectation and so forth. You can do that. But then, so suppose you do this. Say, lambda, let me see, partial mu, all right? Suppose you do this. So this will be the summation I equals 0 to 16 and I, and then log of the pi I here. And so this will be what? 1 over pi I theta and then take the derivative of the pi I, derivative of this with respect to the mean, and then we have a beta here, and then inside what we have what? I mu I minus 1, and then minus the mu I, and the times e to the minus mu. Okay? That's what it is. Okay? And then you take the partial to lambda, well, that's almost the same, except that you change the notation because they're almost the same. Lambda, and then you have the ni, and then instead of beta, you have a 1 minus alpha minus the beta, divided by pi I theta times, then you have an I lambda I minus 1 minus the mu I, and then e to the minus lambda. Okay? So suppose I call this equation 1 and 2, and then you set 1 equals 0, 2 equals 0, and then we get the following. If you set this to 0, and then let me just say this. This implies if you sum it, then you have this summation I equals 0, 16, and I times the I, you have the beta, mu I, and then I put another mu in here because it gives a mu minus 1, right? I just put a 1 in it, pull 1 out, and then divided by pi theta. That's the sum on the other side, and then equal the sum on this side. The sum on this side is the summation I equals 0 to 16 of the ni beta mu I. Oh, I also have e to the minus mu. So insert e to the minus.
That's a constant.
Well, yeah, but the book doesn't want it canceled out. We can, but we don't want to, because the book wants us to prove something, right? So then it's divided by the pi theta. Okay, so now if you multiply mu to this side, divide this is over, what you get? So mu equal summation I equals 0 to 16, and what do you want us to do? Because we have this particular notation. So okay. So here you have the ni. What they want to do is the ni times this whole thing in here. And then this thing, they want to call it the Ti theta. Okay, Ti theta equals this. Ti theta is the beta mu to the I e to the minus mu divided by that. Yeah, that's just this part. And then that's the part, and then here's the sum, I equals 0 to 16. And then here we have I and I, and then you have a beta, all these things, and then here's the Ti theta. Okay? You following me? So then this, of course, 2 equals 0 similarly imply the lambda will be the same thing. So lambda in here will be the summation I equals 0, 16I and I, except that now instead of the TI, they call it the PI theta. And then here is the sum, 16 of the NI PI theta, where the PI theta is the 1 minus alpha minus beta, lambda I e to the minus lambda divided by I. So, so suppose we call these call these 3, call this equation 4. So from the right hand side, okay, let me see this. Left hand side of 3, mu is really mu of the theta, because this is a function of the theta in here. Okay? So mu is really mu of the theta, and then this is, I would just say, the right hand side of 3. And left hand side of 4, lambda is lambda of the theta. This is the right hand side of 4. Okay? So what does it say? This says essentially, with the theta, there's some t on the right hand side. So we've got to update the equation. Updating. Is this. For mu at the t plus 1 is what? Just the mu of the theta at the t. Okay? In other words, this is a function of theta in here. Okay, you have a function of theta, that is alpha, beta, mu, and lambda. So if you put in all these, the pi's and so forth, the Tij is here. The pi I depends on the theta. Okay? And then you got a mu, beta, and so forth. So if there's a theta t in here, of course, is alpha t, beta t, mu t, and lambda t. Okay? So conditional on the theta, of course, and then substitute everything with the theta in there. This is the reason they put it the Ti theta, because all of these doesn't depend on theta. Whereas the Ti theta is in here, because the beta, mu, and so forth, especially here, that all depends on the theta. So you plug in the theta t, all this is given like that. So if you give me this and all the past ones, how do I update? This is how I update it. Okay? This is how I update it. And then lambda t plus 1 is the lambda of the theta t. Okay? And this is from where? From 3 and 4. Okay? So that's how you update it. Now, how do we get the alpha and the beta then?
How does 3 go into the updated lambda?
No, 3 for mu, 4 for lambda.
Okay.
Yeah. So this is from 3, that's from 4. Okay. Okay, so for alpha and the beta, So for alpha and the beta, now consider let, I will just use book notation. Z0 theta be the probability, that a respondent responded by 0 encountered, responded 0 is actually belong to, is actually belonging to the Z group. Zero. When I say Z group or the 0 group, right? Because we have 3 groups, right? The first group, second group, 3 populations. That's our model. So you say the Z0 theta is the probability that a respondent responded by 0 that actually belong to that group. Because other group, because of distribution, they can also respond with 0 also. Okay? So, given theta. In other words, under the theta, particular theta, and then that's the probability. Now, if that's the case, then alpha will be the pi 0 theta times the Z0 theta. What's the pi 0 theta? The pi 0 theta is the distribution that what? How many people actually responded by 0. Now, all these people, say, suppose they say you have 10 people respond to 0. But each one has a certain probability actually belong to that group. So and that is what? That is the probability actually in there. Okay? So this is the number of those who responded with 0. That's a total number. But each of those numbers has a certain probability actually belong to it. Okay?
And the 0 group are the people that lied, like they're gonna say 0.
Yeah.
No matter what.
Yeah. That's what I'm saying. So the Z0, okay, we say the Z0 is the probability. Okay, because not everybody say it belong to that, actually belong to that. Okay? Okay, and then we let also Ti theta be probability that a respondent responded I encounters actually belong to the P group. Typical group of truth, counter truth group or something like that. Okay. So then the pi I theta times the Ti theta is the beta mu I e minus mu. is that the pi I theta are those numbers who actually what? I mean, the TIs is that these are numbers who actually responded with I. That's the probability x equal I, right? So those are actually responded with I, but with a certain probability. But that one is what? Belong to the number belongs to the T group. The T group has this distribution there. Okay? And that distribution times. Okay, that's how that. So from this you already know. So oops. Okay. So N0 times Z0 theta. This is what is the estimated the number of group 0. Group 0. Then an estimate of alpha is what? N0, Z0, and theta. And similarly, and so I'll just say so. The alpha t plus 1 equals N0, Z0, theta t. That's your update. And similarly, summation I equals 0 to 16 of the Ni Ti theta is the total number of individuals who is in So this is the total number which says that we call it I. But this is the probability they actually belong to the group I. Okay? So you sum up all those, and then, those says that I actually belong to the T group. So this gives you what? Total number of people who are in T group, who reported 0, 1, 2, 3 to 16. So the beta should be what? Should be just this divided by total N. And beta plus 1 is the summation in I, Ti, theta T. And this actually is what? Is actually, you can get this actually by conditional expectation. So, as I say, this is the expectation, and the previous one, the lambda and the mu dot updating is actually the N step. This is actually the E step. The other one is the N step. So, E step you get alpha beta. N step you get a lambda mu. So you go back and forth, and that's how you get almost all the mixture problem, almost all these values. Okay. Okay, just a very briefly comment on. Any question on this? Just a very brief comment on the problem, not in the book, but I make up for you. This model rate. This one we will do it by conventional. That is. Oh yeah. Okay, maybe I should just stop here. Okay. All right. there, of course, what you have to do, you have to do the conditional expectation of the z. You know, some of you still use the ti. No, not the ti. The ti is what? It is actually what's given to you. And then what you have to do there is that you conditional on the z because it's some kind of sensor. So our notation is that we use what? We use y as the compute data, x is what you see, z is what you don't see. So all the sensor data we should call it the zi. Okay? So then what you have to do is find the conditional expectation of the zi, given that the zi greater than ci, whatever that sensor is. And then you see what that is. And then not only that, you have to say because it's squared there, so you have to also find out what the conditional expectation of zi squared, given the x and the zi greater than ci. So you have to calculate those things. You know, those things, if you know what to do and so forth, well, you have to do some algebra. Okay? And then one more trick there is the following. You know, you can exchange the integration and the expectation. You know, integration and differentiation in this case is good because what? All the TI are conditionally normally disputed. Okay, so everything is normal. So you can almost do anything you want. I mean, all the conditions will be satisfied. You can exchange this, rearrange that, you know, all these are no problem. So instead of, say, take the expectation of these things, you can differentiate first. Because once we have this Q, you want to do the partial differentiation, right? So actually, you can do the differentiation first, then take the expectation. That can simplify the problem slightly. Anyway, I will get into these next time. Okay, I'll stop here.